It's my pleasure to present our next speaker, Roberto Negrin. Roberto Negrin is a PhD student at Alice Bob Paris, working in CAD qubit calibration, optimization, and continuous quantum measurement. Roberto earned his master's degree in quantum science for USC, University of California, in LA, and focuses on bridging theory and experimenting for robust bosonic qubits. His talk, Inside Cat Qubits, Physics, Implementation, and the Road to Fault Tolerance. Thank you, Roberto, to having with us. You can proceed with your presentation.
Thanks for that introduction. So let me share my screen. Oh, my name is Roberto Negrin. I'm Chilean. I will do the talk in English, but the questions can be in Spanish if that's easier for you guys. It's more personal, so we can do it in Spanish. Uh, I work at Alice and Bob. Alice and Bob is a French company. I'll tell you more about it in the next slides. But today I want to talk to you about cat qubits. Inside cat qubits, this interesting technology that maybe some of you haven't heard before, and explain you a little bit about the physics, about what we do in in our daily life, and also some of the tools that we use. I hope you can hear me and see everything well. So assume and continue. So just I'm gonna talk to you first about the company, who we are, what we do, then about the physics of these special types of qubits, and some of the gates that we perform and the requirements that those gates have, because they're not that simple. Then I'm going to show you some of the tools that I personally use, and also some examples on performance of these cat qubits. And finally, I can answer some of your questions that you may have after the presentation. So just to give a brief presentation about myself, I'm currently a PhD student at Alice and Bob here in France, in Paris. They have this interesting way of having PhD students inside companies. So I can be inside a company while I do my PhD, which I find super interesting because it allows me to get industrial experience and at the same time work on my PhD. I'm working currently on cat qubit optimization, which means how can we take the most of the systems we already have, and continuous quantum measurement. This actually means just read everything that comes out of the qubits and do something about it. So I read everything that comes out of the qubits and I try to optimize that. It's a very interesting work, and it's the current development of my PhD. So a little bit more about Alice and Bob. Alice and Bob is a quantum manufacturer. So we built the chips. We do have small algorithms and application teams, but our main goal is to bake the chips. We work with superconducting technology. You probably know already that there's many ways you can make qubits. One of those ways is superconducting qubits. But even inside superconducting qubits, you have different architectures or different technologies that you can use, or encodings, as you want to call it. And inside those, we work with a specific one that is called cat qubits. That's why the logo of the company is a cat. And the main goal of Alice and Bob is to focus on fault-tolerant quantum computer. So we want to create a quantum computer that is fault-tolerant, like error-proof. And this is a very hard task right now. So Alice and Bob is a quite new company. It was created in 2020. But right now, this year, we raised more than $130 million to help us build these cat qubits. And we are currently more than 120 employees. I would say even more than 150. We're growing quite fast. And we have some partnerships with important companies like Google, NVIDIA. We use NVIDIA mostly for GPUs and connecting GPUs with the qubits, and also Microsoft. So what is a cat qubit? First of all, I want to explain to you the main idea behind them, which is escaping from one type of error. So usually qubits, you probably know, that have two types of errors: bit flip errors and phase flip errors. And most of the current qubit architectures try to correct for both at the same time. Because most of the time, the ratio of those two errors is quite similar. I have the same amount of bit flips that I have of phase flips. But what would happen if we could suppress one of those? What happens if we can make one of those be close to zero and we can only focus on correcting the other one? So that's the main idea behind cat qubits. What we do is we try to, by architecture, by design, eliminate one of those errors and only focus on correcting the second one. In our case, we specify on bit flips. So we try to completely eliminate bit flips. And that allows us to focus our error correction in phase flips only. On the right, you can see a small graph of how our bit flip time has evolved during time in the last 5 years. We started with a bit flip time of around milliseconds. Um, this is 2024, it's outdated, but in 2024, we got bit flip times of minutes, so 1 minute without getting a bit flip error. And a couple of weeks ago, almost a month ago, we got our latest result, which was a bit flip time of 1 hour. There's not a paper on that still not a paper on that, but there's a nice blog post in our webpage if you guys wanna find out how we did this experiment. So don't get me wrong, it's 1 hour without having a single bit flip. That's quite impressive. But how do we do this? Like how do we create this the difference between phase flips and bit flips? Like there's just many architectures you can imagine, or like what's a CAD, white cats, etc. So a CAD is a very specific encoding of a qubit. What do I mean by an encoding? What I mean is like we will take some states and we will say this these states represent our qubit. But we won't take any state. We will take coherent states and superpositions of coherent states. Just to remind you, coherent states are a weighted sum of all the possible excitations of an harmonic oscillator. And it's a specific weighted sum with a Poissonian distribution. It's quite a special type of state, which usually has classical properties. But the good thing is that when we treat those states and the superposition of those states, more specifically, we can create these new ones that are called cat states. So we can create a cat state by adding two coherent states and by subtracting two coherent states. And these cat states will have quite interesting properties, as we will see after this. One of the main difference between a cat state and other types of transmon qubits is that here we want our oscillators or cavities to be harmonic. We want all these separations to have the same distance, all these energy levels separations to have the same distance. Usually in other types of superconducting qubits, what we do is that we separate, we separate the energy levels in a non-equivalent way to encode the qubit in the 0 and 1 states. But here we want them to be harmonic. We want it to be separated the same. But how do we make this cat qubit? Well, here on the bottom left, you can see a small picture of our chip. Don't get super lost. I just want you to get one big idea out of this picture. I want you to get the idea that our cat qubits are made out of three main blocks: the memory in blue, the buffer in red, and what's called the ATS in yellow. I will explain you the details in the next slide, but just like a big summary, these three things contain our cat and the interaction with the cat and the environment. So in the memory, we will save the coherent state. We will save this alpha, this minus alpha, and these superpositions. And the buffer, the red thing, is what connects the cat with the environment. It's like the line that allows us to interact with the cat. But this interaction is mediated by an ATS, which is a very special interaction that has specific properties to maintain these cats. I will get into those details in the following slides. But from this, the three ideas are: we want coherent states, we want harmonic oscillators, and we have this architecture that it's composed by three blocks: memory, buffer, and ATS. So does this really work? Is the main question. So there's a lot of we have gotten a lot of experimental results in the last couple of years, in the last 5 years since the company was funded, and the short answer is yes. With cats, what you can do is that you can suppress bit flips exponentially while only increasing phase flip linearly. So I'm decreasing one error exponentially and I'm increasing the other one just linearly. So I can suppress way more than I create errors. If this looks like a line to you, is because this is in a log scale. So if this was in a normal scale, it will look like an exponential. You can see here that um, this suppression increases or improves with the number of photons that we put in our cats. So the number of photons is basically the size of my cat. If I have a big cat, if these blobs are very separated, then I will suppress more the bit flips. If the cats are small, the blobs are close to each other, then I will suppress less the bit flips. And if you see here, we reached a saturation point where increasing the size of the cat does not improve the bit flip. This is research that is currently being done. We are trying to investigate why this is saturating. But this saturation point has improved over the years. So we are able to get better and better bit flips. So quick summary here. What you need to remember is that a cat qubit suppresses bit flips errors exponentially and increases phase flip errors just linearly, which is actually very good. Why is it very good? So what happens? What we do in this case is that we will have two types of error correction, of two types of error suppression. We will have an autonomous bit flip suppression that will come just from having cats. So my cats will suppress my bit flips. And then we can do some error correction techniques to suppress those phase flips. By error correction techniques, I mean a simple error correcting code like the repetition code. It's a 1D code, which requires way less qubits than other systems. So just to give you an idea why cats are so efficient, maybe some of you remember Google's experiment last year where they showed a logical qubit under threshold. For that experiment of distance 7, they used 105 transmode qubits. Replicating the same experiment with cats will take only 13 cats. This is research that is currently under testing inside the company, but it's just to give you an idea the amount of reduction that we have in qubits. And less qubits means easier scaling of our systems and means reaching fault tolerance faster. Now, why does a cat qubit create this suppression? Well, it's a hard question, and we will dive a little bit into the Hamiltonian of this system. I will try to make it not super technical, but there's some technical stuff that we can look at. So again, we have our three-part system: our buffer, our ATS, and our memory. In the memory, we save the cat. In the buffer, we interact with the environment, and then we have this ATS. This ATS has one specific property, which is the important one. It is that it exchanges photons between the memory and the buffer, but it's not both ways. It's not the same both ways. What I mean is like it exchanges one photon of the buffer for two photons of the memory, or two photons of the memory for one photons of the buffer, one photon of the buffer. So it's a 2-to-1 interaction. And this 2-to-1 interaction will have interesting properties that will allow us to create this bit flip suppression. Then our buffer interacts with the environment, and our memory, even if we don't want it to, our memory also interacts with the environment. It's noise, it's loss, what it's called. So this is not good for us, and this is actually what will create the phase flips. This interaction with the environment is the one that creates the phase flip. This can be reduced by manufacturing procedures, but it will most of the time always be there. So we need to learn how to improve it as much as we can, but also correct it in an active way, like error correcting codes. So this system can be represented by this Hamiltonian, more or less. Um, the ATS will create this two photon interaction with this G2 component. And you can see, for the ones familiar with creation and annihilation operators, that creating two photons on the buffer only takes me one photon of the memory. Sorry, the other way around. Creating two photons of the memory only takes me one photon of the buffer, and then destroying two photons on the memory only creates me one photon on the buffer. It creates this 2-to-1 interaction. Um, and why is this Hamiltonian so special? Like, by looking at it, doesn't really look that special. It is special, and we can analyze what is called like a semi-classical analysis of this Hamiltonian, and we can represent it as a potential. We can visualize this Hamiltonian that I just showed you as a potential, which is the potential that is presented in this image. You can see that this potential, it has two holes, one in alpha and one in minus alpha, and it's separated by a wall. What does this tell me? It tells me that going from the state alpha to the state minus alpha, it's quite hard because I have to go through this wall. This is why this Hamiltonian creates this suppression of bit flips, because a bit flip in my code space will mean going from alpha to minus alpha. And if I have a wall in between those two states, then it will be harder and harder to cross that wall. And it's even more interesting because the height of that wall or the depth of those holes depends on the size of my cat, of the value of alpha. So bigger cats create holes that are deeper or walls that are higher. So it makes it harder and harder to cross from one state to the other. So the main reason why I showed you that Hamiltonian before is because I wanted you to link that Hamiltonian with this potential. You can think about this potential as this like a semi-classical representation of that Hamiltonian. And this is a very visual way of seeing why cats suppress bit flips. You never want to jump from one from one hole to the other one. Now, this sounds very nice, but I think many of you may be wondering, uh, if I apply a gate, for example, a Hadamard gate, my face flips now transform into bit flips, and my bit flips now transform into face flips. So how does this work when I'm in a different basis? How does it work? Like if I go to the plus state, then my bit flips are face flips, and my face flips are bit flips. So now my noise bias is completely destroyed. So that's a good way of thinking. But we can make something that is called it's called bias preserving gates. So a bias preserving gate is just a gate that doesn't destroy this beautiful property that we created with cat qubits. So how does it work? How do we actually make this? So it's you can think about it. This is it's not exactly like this, but it's a good way of thinking about it. You can use higher dimensions to go from one state to another without breaking the bias of our system. So usually in a normal qubit, you are restricted to only state in the surface of this block sphere. So doing a gate that goes from the state 0 to the state 1 will require you to pass through the equator of this block sphere, right? And in the equator of this block sphere, phase flips transform into bit flips, and bit flips transform into phase flips. So if you pass through the equator of this block sphere, you're gonna completely destroy your noise bias. It's gonna break. But what we do with cat qubits is that I don't if you remember that I told you that we were using all the states of this harmonic oscillator, not just the 0 and 1. We can take advantage of that property and kind of go out of the block sphere, avoiding the equator and going into the state that we want to reach. You can think about it as going out of the block sphere, as going through the block sphere, but it's kind of to give you an idea. So since we are not restricted to this sphere anymore, to this block sphere, we can create bias preserving gates. It's not easy. I'm not saying it's easy. It's quite hard to find these gates and to implement them, but they are available for us if we need them. An example of this gate will be a CNOT gate. If you don't perform a CNOT gate in the correct way, it will not be a bias preserving gate. Um, but there's ways of doing these bias preserving gates in CAD qubits. And the CNOT gate is one of the most important gates that we have because it's required for error correcting codes. So without a CNOT gate, basically any qubit is a little bit useless if you wouldn't be able to do error correcting codes. So in the right, you can see two cats, and this is experimental data of a CNOT gate into cats. Of course, the fidelity needs to be improved to make this gate as accurate as possible to be able to do error correction. But this is work from last year. In this last year, this research has improved. And this is the example of a gate that is bias preserving, that in a naive implementation will not necessarily be bias preserving. So now I'm gonna guide you a little bit. I'm gonna talk to you a little bit about some of the tools that I use in a daily basis. So for me, my most precious tool in the last year has been Dynamics. So most of you may probably familiar with Qtip. Qtip is like what we usually use when we're in school and we want to do simulations of quantum systems. Even if it's not quantum computing, just any quantum mechanics simulation will require probably Qtip. So Dynamics is kind of similar to Qtip. It allows you to simulate Schrödinger equations, master equations, stochastic master equations, any type of quantum master equation that you can think. But it has some benefits compared with Qtip. The first one is that it has GPU support, so it has an improvement in performance and allows you to do batching. So batching is when you run multiple parameters at the same time using either CPU or GPU. But for example, let's say you want to test the system, and you want to test a cat, but you want to test different sizes at the same time. This is super easy to do with Dynamics. You just give all the sizes at the same time, and you can run it automatically. The other important tool that's especially important for me is that it's differentiable. So you can literally take the derivative of your Hamiltonians of your systems. Why is this important? Today, where everything is machine learning related, having differential simulations is key. We simulate our system, we can differentiate, we can plug this in an optimizer, in a neural network, in many pipelines that you can imagine. So differentiability is one of the most important features in simulating quantum systems in right now, at least in my opinion. And what is good is that if you're already using Qtip, it's quite easy to go from one to the other because interfaces are quite similar. So now I wanted to give you like a super brief demo of it's not about dynamics. That one will leave it to you for you to test. I just want to show you some of the advantages of CAD qubits with a small Qiskit simulation. So what we're gonna do when the idea of this small demo is to show you how much better is the bit flip of a CAD qubit respect to another transmont qubit. So let's start by just making the simplest circuit you can imagine. What are we doing here? We're just preparing a state 0. We're applying a NOT gate and we are measuring. So what do we expect to get in a perfect, this is a perfect circuit. It doesn't have any noise. We expect to get a value of 1. We expect to get a state 1 all the time because it's a perfect circuit. Now, if we do something similar, but we have a Hadamard gate instead of a NOT gate, the Hadamard gate takes the state 0 into a superposition of 0 and 1. We can repeat and we will expect a superposition. But as I said, this is a perfect circuit. It doesn't have any noise. And in reality, this is not exactly the case. So now we're going to load a fake backend. I'm not connecting to a real system, but these fake backends, what they do is that they imitate some system's noise. It's going to take a couple of seconds, nothing too slow. Okay, so what we were doing here is we were again preparing the state 1, which we got 100% 1 without noise. And now we can see that, okay, it's quite good. It's 1 983 times, but I start getting some zeros here, right? So I'm seeing some errors already in my code, in my circuit. And those errors, where do they come from? They can come from many places. They can come from how do I prepare my state? How do I prepare for my gate? How much time it passes between preparing my state and measuring? And even how I measure my state can have errors. All those things can induce errors. And as we can see, as we will see, these errors will get even worse with time. For example, here I'm preparing my state in a one
Roberto,
state. Yes.
sorry for interrupting to you, but we can see the slides for that say demo.
Oh, you have not been
Yeah,
seeing the demo?
we can see the demo. We still can see the only the slides.
Oh, that's bad. Okay.
Yeah,
Okay, sure. Now?
no, it's good. Thank you.
Okay, so I will go all over again. Someone should have told me before. It's okay. Well, I may be repeating myself, but let's go again. So we will make the simplest circuit we can make. We prepare a state 0. We measure x. Sorry, we prepare a state 0. We apply a NOT gate, and we measure. What do we expect? We expect to get only a state 1, which is what we get. Now, if we do the same thing, but instead of an X gate, we apply a Hadamard gate, we would expect a superposition of 0 and 1, because this is what the Hadamard gate does. And we actually do get something like almost like that. This is still probabilistic, but it's around 50-50. Now what we will do is we will do the same circuit as the first, but we will add some noise. We will take a fake backend, which what it does, induces noise, fake noise into my system. And we will run the simplest circuit ever, just an X gate, and we will see how it performs now. Do we only get once, or do we get other other states? So we see that in most of the time we still get 1, but we already get a couple of 0 states. And this is due to many types of error, as I said, measurement, preparation, etc. And this gets only worse with time. So if I add now a small delay after my preparation, we will see that these errors will increase. Okay, so look carefully. What we're doing here is we are preparing a state 1, we are waiting, and we're measuring. And we can see that most of the time, my final result wasn't state 1, was state 0. What is happening is that most likely the qubit is decaying from excited state to ground state. It has some physical property that makes it decay after a certain time. So this is something that we want to avoid. We want to prepare a state 1. We want to wait as much as we want, and then we want to measure, and we want to make sure that the state at the end is still state 1. We don't want it to go back to 0. So that's when we have cat qubits. With cat qubits, what we get is, after using the same circuit but with a different noise model. Here I'm using a noise model that is from Alice and Bob. What it does, it imitates the noise of a cat. So here I can tell the noise model, take me a cat with 11 photons, which looks like this specific cat, because we have different systems. Different systems have different noise models, etc. And I can run the exact same circuit that I did here. I can run it with a cat noise model. And you can see that in this time, 100% of the time, I get a state one. So you say, okay, this is really good. Like let's just start using cats. Like here, everything failed, and here everything was okay. But as I show you before, as I told you before, this this correction, this protection is only for bit flips. If now I look at phase flip, so how do we look at phase flips? We do a rotation, or we prepare the state plus, and we measure in the X basis. That will tell me the phase flip. So I rotate and I measure. If I do that for a cat, what I get is I would expect to get only once, and I get a mix of 0 and 1. So this is quite bad because I was trying to get only ones and I'm getting zeros and ones. So from here you can get that there's one dimension bit flips that are really protected compared with a normal transmon. But there's another dimension that is phase flips that are not quite protected, that they're actually performing a little bit bad. So this is why we need also error correction. Error correction is another layer that will go on top of our cats. We will do repetition codes, performance, surface codes, etc., to improve these phase flip errors. But that's a story for another day. It will take me way more time to go through error correction. So it's important for you to know that we still need it. Like cats are not perfect. We need error correction, but at least we need way less correction than other types of qubits. Um, Thank you. That's the end of my presentation.
Thank you, Roberto, for your excellent presentation. We have some questions for the public.
Yeah.
Can you describe a moment in your research when you felt particularly excited about the potential of cat qubits?
So yeah, as I was telling you, like a month ago, we had this great breakthrough where we got more than one cat, many cats to reach more than 1 hour bit flip time. I think that that's a very big accomplishment, and it's a big jump from what we had last year. So that felt for me and for the company like a big achievement in the last couple of months, because we were a little bit slow for a year, and then we got this good breakthrough, and that helps lift the morale and everyone's hopes at the end of the day. But yeah, that's the first one I can think about in the last couple of months.
Thank you, Roberto. How has your experience studying and working across different countries, United States, France, shaped your approach to research and collaboration?
So so first of all, as a Latin American in the US and in Europe, you have more barriers, but it also opens more gates in the sense that you're always open to collaborate with Latin America, which some other people may not be that interested in. So you always have Latin America's door open. Um, I think what it does, it broadens your mind to just collaborate with anyone, and don't have any prejudice about other people. So that's, I think it extends your world more than just staying in Latin America, also just staying in Europe if you're a European, like just moving around, knowing different people from all over.
Thank you, Roberto. Are there open source tools, simulation platforms, or educational resources related to cat qubits that could be adopted by university in Latin America?
Yeah, so Dynamics. Dynamics, as I said, is it's a baby inside the company that was made for by three PhD students inside Addis and Bob. It took some time to develop. It was made out of necessity, like they were using Qtip and other alternatives, and it was not enough. It was not differentiable, etc. And then they made this. It's an open source tool. Everyone is open to collaborate. It's amazing for simulating quantum systems. I use it literally every day. It's in development, but it's always improving. And since it's a small group of people who are developing it, they're always open for suggestions and requirements from the users. So if you have a specific use case that you want to see if it's possible to implement in this platform, um, it can always be implemented. And I think so. While I was studying, I used a lot Qtip, and now that I use Dynamics, it gives me way more freedom to do stuff. So if I would do all those, if I could do all those homeworks again with Qtip, with Dynamics, I would be more than happy. So I would suggest universities in Latin America to start using it as an educational tool to simulate systems, to visualize Wigner functions, to visualize trajectories, to understand measurement, heterodyne, homodyne measurements, etc., etc. It's a really good tool.
Thank you. Have you had mentors who guided you through the complexities of quantum research?
Uh, So yes and no. So yes, there's always I cannot think about a specific person, but the good thing about my company and right now is that it's not that big. Like we're just growing, so you can always find someone for the necessity you have. Like if you have a problem with a specific thing, there's always someone more than happy to help you with that. If we go even back in like my educational life, yes, like this, I was always a big fan of science education in internet. So there's a lot of science educators that I always inspire me to go into physics. And I think it's important for new generations to be familiar with that. But yeah, I would separate those two things. Like one is the daily life, and the other one is more um, career path motivation.
Thank you. How did they influence your career path?
Um, let's start with so my career path is a little bit mixed. I studied engineering in Chile when I was in the third year of engineering. I switched. I didn't switch. I did also physics in parallel, and that switch was made basically because of the amount of physics that I used to consume in the internet. So I used to consume big quantities of books, of videos, movies, and I thought it was just a hobby. And then at some point, I realized that maybe it wasn't just a hobby. And I think without the amount of information that was available for me at that step, I wouldn't have been able to make that decision. So they basically moved my career towards physics in that sense.
And another question: how do theoretical models guide experimental work in your lab and vice versa?
Okay, that's a good question. So yeah, there's there's many there's many approaches people can take. I would I would divide them into three maybe. There's the approach of let's do an experiment and then we explain it with a model. Then there's the approach of let's have a model and then we develop an experiment to test it. And then there's another one that it will be more I don't know if so many people have it, but let's make an experiment and we can explain it or not. We don't really care. We just care about the results, right? More more interested in the results than in the model. So I think the first two are internal discussion, or more than inside the company, depends on people's personality. For me, for my work, is very model based. So I really need to understand the physics of the experiment before doing the experiment, because I do a lot of optimization and fits of experimental data. So if I don't really have a fully understanding of the model, then probably my fit is going to fail. Like my work is not gonna end up well. So I will say it depends a little bit of your position inside the company and also of your philosophy towards work.
Thank you, Roberto. Are there opportunities for joint research projects, internships, or virtual collaboration with Alice and Bob that could benefit LATAM students?
So yes, so there's a lot of internships at Alice and Bob. Um, the main issue is that for internships, Alice and Bob does not sponsor the visas, which is a little bit more complicated. For non-internships, for full-time jobs, I guess I don't want to say anything that it's not true, but I think for visas are sponsored for full-time jobs. For students, the best way is to go through an internship. It's in discussion how to manage cases outside the European Union because right now those are the only ones that don't require a visa. But I think there's always also interest in having academic uh, alliances between Alice and Bob and other type of partnerships outside. Through PhD students like me, I'm a PhD student. I have more freedom. I can interact with or do research with Latin American universities if a good project is presented for both of us. So PhD students are a good link to connect, but to go the other way around from Latam to Alice and Bob, I think it depends a little bit on your citizenship situation.
Thank you, Roberto. Were the moments where experiment results didn't match theory, and how did you overcome this challenge?
Yeah, every day. Every day experiment results don't match theory. But the ones that have the final word are experiment results. You cannot say that the experimental result. I mean, yeah, sometimes there's errors, but most of the time you cannot say that the experimental result is wrong. Most of the time, it's the theory that's wrong, and most of the time it's not completely wrong. You have something off. Again, I think there's two approaches to this, similar to the one I mentioned before. There's a team that will say, okay, let's take the results, let's dive into the theory and find the reason why we're failing. Let's explore every single theoretical case and see why this is not working properly. And then there's another that is, okay, let's take more like a what's called a black box approach, which is like we don't really care about exactly all the terms where they come from, but we only care that it works well. I'm in between. I think I'm in a case to case. Some cases I think it's important to really dive into the theory again, understand some of the approximations that you did maybe weren't correct, or they were too naive. You did an approximation that is actually not true. Those are details that you can always check. A very good tool is simulations. Again, simulating your systems is always good, and comparing the simulations with what you see. Because looking at an equation, it's nice, it tells you something, but looking at a simulation and compare it with the real data, it's for me one of the best ways of debugging models. So that will be my approach. And no, there's always someone inside the company. There's always someone that knows more than you. So there's always someone you can ask for help also.
Thank you. What skills or habits has been most important in bringing theory and experiment in your work?
Okay. So personally, I didn't have many experimental background before joining the company. Mostly theoretical. I mean, experimental background just from school, which is not, it's a couple of courses only. So for me, the experimental side has always been complicated. Um, but I think the most important thing in my case has been finding a sort of mentor, as you said before, for a specific area. So if I need someone that helps me how to do experimental stuff, I will find a mentor in the experimental side. The same in the theory side, the same in the optimization side. Uh, and I don't want to repeat myself, but also doing simulations helps me to understand way better the experimental outcomes. So being able to simulate the system, what happens if I change this parameter just a little bit? I see how the simulation change. What happens if I change this other parameter? So it allows you to make a map between parameters, equations, and signals that come out of your system. So you can see how the signal change depending on how the parameters of your simulation change. And this is very visual, and it's a really good way of understanding the experiments.
Thank you, Roberto. Um, what would a roadmap look like for a Mexican university to introduce advanced course on bosonic qubits, CAD qubits, or hardware efficient error correction?
Okay, so those are different, very different courses. But in my experience, what you need, bosonic qubits, you can think about them in different ways. The most straightforward path would be to start with an open quantum systems course for students. But before an open quantum system course is already a little bit advanced, you already need quantum mechanics to go for an open quantum systems course. Um, but I think inside an open quantum system course, you can discuss CAD states and CAD qubits and bosonic qubits in general. But I think so. The way I see quantum computing right now, it divides in two branches. You have the theoretical physical branch and the algorithmic error correction branch. Even that one you can divide it in two. You could have physical error correction and algorithms. Um, I I don't see those three. Maybe algorithms and error correction, they touch themselves a little bit more, but sometimes the physical branch can be a little bit separated. It can try be treated isolated. So just having a big understanding of the physical system, even if it's not completely related with qubits, right? Just having a good understanding of open quantum systems can help you a lot. For me, it's important to have these three blocks. So I think the main decision is: do we want to take all of those blocks into our program? Do we want to specialize in one of those blocks? And then you need to do a gradual course improvement, in the sense that you need an introductory class, and then you need a medium class and an advanced class. And in each of those classes, you need to make more decisions again. Do I only specify myself? Do I only restrict myself to a certain type of qubit, or do I teach the general physics to understand all types of qubits? I will go for the second one. In my opinion, it's way more important to understanding the general physics to understand all types of qubits. But I think it's important to separate those three branches. Apart from that, I'm not sure. Those are my main ideas on the topic. The way I would do it.
Thank you, Roberto. From your perspective, what are the key challenge remaining before we reach truly fault-tolerant quantum computing?
So the main challenge for me is scalability. Scalability. We can have one qubit that performs one logical qubit performing on the threshold, like the one I showed you about Google. But that logical qubit, maybe I can go to my slide. Um, if you remember, one qubit took 105 transmons. This means 105 transmons. Each of those transmons has cables connected to them that go inside the fridge that need to be calibrated. Not only the qubit itself, but the connections between them. Imagine scaling this to 100 logical qubits, or 1,000 logical qubits. The amount of cabling, the amount of connections. That's the main problem that I see in the fault-tolerant quantum computing for more traditional types of qubits, right? Transmons, trapped ions, etc. For CATs, we are now fighting against repetition code. So once we implement repetition code, we will see how hard it is. But we also have problems of scalability. Like, we have less problems of scalability, but they're still there. The cabling, the connections, the calibration is it's there's in this paper of Google, there's a picture, or there's a diagram of the calibration graph of the system, and it's a huge graph full of measurements that they need to perform in advance just to calibrate one qubit. So calibration is a big roadblock in fault tolerant quantum computing. So I would put scalability of the physical system and calibration as the two main issues in that sense.
Thank you, Roberto. Are there opportunities for Mexican PhD or master students to contribute remotely to Alice and Bob projects while gaining practical experience?
So for remote, I would have to say no, and I will justify it because Alice and Bob it's inside the European Union, and it has some restrictions on information information that can be shared and cannot be shared. And even inside the company, when we travel, there's the security the measurements that need to be taken. So we're restricted in the sense that there's a lot of sensitive information that cannot be spread. So I wouldn't say that it's possible to generate as a as contributing directly to the company. But again, I think for especially for PhD students, they could be shared projects between PhD students. For example, me and a PhD student in a university in Mexico, that they act as co-authors or authors in papers with or in research with Alice and Bob, and that's been done from other universities in different parts of the world, and it's something that could be done.
Thank you, Roberto. Uh, how Alice and Bob engage with the academic and startup communities to foster innovation and education in quantum technologies.
Okay, so in Latin America, not much. That's one of the reasons that I wanted to be here as a Latin American. I wanted to participate in this event. It's a because Latin America is quite a foreign market for Alice and Bob. In general, with the academia, the best way that Alice and Bob has is as with through PhDs like me. Through PhDs, we work some time at the university, some time at the company. So we create a link between company and academical partners. So you have professors that more or less work for Alice and Bob. They don't really, but they have PhD students that work for Alice and Bob, right? So they transmit their knowledge to the company towards the PhD students. And I believe that this is a very valuable resource. Most of the, not always, but most of the time, big breakthroughs come from PhD students inside companies because they have more freedom and they have more flexibility and less deadlines towards so they are allowed to explore and some of the biggest breakthroughs in Alice and Bob have came from PhD students. So I think that's the way they interact with academia, and I really value that. In a sense of with other startups, I think that goes a little bit out of my expertise. Um, of course, there's classical things as fairs and always a connection between other French startups in quantum and in this French programs or European programs for startups. But I wouldn't have been. I'm not able to specify the exact program for that.
Thank you, Roberto. What are the main challenge in calibrating and optimizing CAD qubits for large-scale computation?
Okay, that's a good question, and it goes more into my area. So the big challenges we kind of already talked about them. The main challenge is matching with uh, with the experiment. It may sound easy, like I have this Hamiltonian that I showed you, and it's just plugging the Hamiltonian into the simulation, and it should match. But there's many things you have to think about when you want the data to exactly match the simulation. You need to worry about the cables, the amplifiers that you may have, the waveform generators that your system has. There's like a series of steps that goes from a simulation to a data set in terms of like an experiment. That's the main challenge in the theoretical point of view. being able to model all the properties of the entire system, not only the chip, the entire system. That was challenge number one. Challenge number two uh, starts being scalability in the sense that I told you about these calibration graphs. When you have more qubits, you need to calibrate more of them. But you don't only need to calibrate more qubits. Those qubits start talking with each other. Like it's not an isolated qubit anymore. You have systems connected to each other, talking to each other. So adding more qubits means adding more complexity to your calibration, adding more steps into your calibration graph. And this takes time. For each of those things, you need to run an experiment, which will take 1 second or 50 seconds or 1 hour or 3 hours. But if you have to run 100 experiments, that adds up. And yeah, those are the two main things I would describe.
Thank you, Roberto. How it is preserving the states even after the lie, as in the example.
Sorry, I think I didn't follow the question.
Yes, I repeat, how it's preserving the states even after the lie, as in the example.
Like in the demo?
I think in the demo.
How is preserving the states even after? I still don't quite follow the question. It's in okay. Maybe they can do it in Spanish if they want.
Mm, sí, sería que cómo preserva los estados después del delay, como en el ejemplo, supongo que es
Okay.
en tu simulación.
Yeah. Okay. After okay, I got it. So the first example is with a normal IBM backend, fake backend. So it has the noise model of transmon qubit from IBM. It has a specific noise for preparing gates, for delays, for measurement, etc. The second example, what we're doing is we're using a noise model from Alice and Bob. This model replicates how a cat looks like, what the cat's performance is. So for IBM, we see that after this delay of 1 millisecond, most of my states that I wanted them to be in one, they go to zero. In this case of the cat qubit, this is a representation of a cat qubit. 100% of the states stay in state one. Why is that happening? It's because of this property that I explained about suppressing bit flips. So we are separating these blobs as much as we can, and the states are not being able to jump from one side to the other of this wall in this amount of time. If I wait more time, they will start decaying, but it will take a long time. So what I do is I change my qubit for it to call it. I'm now using a cat qubit instead of a transmon qubit, and that's why my bit flip is way longer. But if I look at the phase flip, well, the phase flip is not longer for the cat qubits. It's bad. It's as bad as a transmon. So that's why I said that it's only one dimension that gets corrected and not both of them. I hope that answered the question.
Thank you, Roberto. Given your success and rapid growth, what skills or backgrounds does Alice and Bob value most when hiring new team members?
Yeah, this is a good question. Of course, there's a technical base that is always necessary. Like you need to have a minimum knowledge about what you're doing, but I wouldn't say that's the most important one. I think the thing that they value the most, I can talk about my example. The thing about what they value the most about me was desire of always been learning something new. You're gonna get here, and I've been for more than a year in Addison Bob, and every day I learn new things, and I feel like I don't know anything. But then I look back of how I was a year ago, and I've learned a lot. But it's this ability of, or it's, I don't know if it's an ability or a desire of always try to learn something new. Never like feel like you already know what you need to know. If you show that, I think people will bet on you because they will say, okay, and maybe he doesn't know this right now, but if I give him 1 month, 2 months, 1 year, or 3 years, he will be able to learn about that. So I would go with that one. That one is my magic trick.
Thank you, Roberto. How do you see Mexico or Latin America contributing to the global quantum ecosystem in the coming years?
I think Mexico and Chile, for example, both of them are big important countries in Latin America. They have a good um, theoretical academical background on quantum and quantum technologies and quantum computing. Academia is going faster than industry. Um, so I feel like we have, as Latin Americans, we have to start moving forward on industry. It cannot be that most of quantum computing companies are in Europe and in the US, and basically a couple of just a couple of them in Latin America. So I think we need to keep pushing in the academical side. We need to keep forming keep forming students, PhD students, but also focus a little bit on the master student that wants to go to the industry, that doesn't want to do a PhD. I feel like that is a very good. That was my idea in the first place. It changed after a while, but that is a very fast way of creating qualified people that can work in the industry in topics like quantum computing. A master student that it wants to work and wants to implement what he learned on his masters into the industry. So what I see in the next coming years, I hope that industry starts growing. I feel like it will, because if there's an opportunity, people will take it. So if where there's an opportunity, someone will go and make something about it. And I think academia needs to start forming this intermediate level students. I don't want to say like that because it doesn't sound that good, but like non PhD quantum workers, which is it's faster and allows you to progress faster too. Like if you have a qualified workforce faster, you can grow companies faster.
Thank you, Roberto. And finally, a question. How can Mexican educators integrate the latest research on CAD qubits into undergrad or graduate curricula without access to experimental labs?
Okay, so I will say two things. First, not even adding the latest results, just adding CAD qubits into curriculum. It's quite nice. I didn't hear about quite qubits during my master's or my undergrad anyway. So I think CAD qubits are usually left behind when people explain qubits, and I feel like they're a very good resource, not to only explain qubits, also to explain open quantum systems, to explain code spaces of different qubits. Like they're not only a qubit, they're a very complex quantum system, so they could be included in a non quantum computing class, also in a more quantum physics class, especially for grad level or masters or a late undergrad. How to do it without access to real chips? Well, we used to have one chip in the cloud. I think it's being updated, so it's not currently on the cloud anymore. But those are tools that could be used. And I will, well, now that I have the slide of dynamics, this is exactly what we see on the experiments. These types of, this is a Wigner function of a cat state with some parameters of a coherent state, sorry. Using simulation tools is a very, very visual and interesting way of teaching quantum mechanics, which can be sometimes a little bit abstract and hard to see. So without access to real experiments, I would stay and spend a lot of time with simulations. I think it's an amazing tool.
Thank you, Roberto, and thank you so much for joining us today and presenting all the developments are working on Alice and Bob as dynamics and answering all our questions. We hope to see you at more events.
Thank you.
Thank,
Gracias.
gracias, Roberto.
Chao, chao.
And Now we will take a short break. Return at 11:45 with Jordan Sullivan from Unitary Foundation. Stay tuned so you can don't miss his talk. Thank you so much.